Well, we have a question here, question 2. The question says, given the following geometric sequence, 30, 10, 10, 30, 10 over 3, dot, dot, dot. Question 2.1.1 says, determine the nth. Determine n if the nth term of the sequence is equal to 10 over 729. Well, in this situation, I'm gonna write here question 2.1. Okay, so we're looking for 2.1.1. We're looking for n. Okay, if the nth term, which means Tn, the nth term Tn is equal to 10 over 729. Well, the question says that this is a geometric sequence. By that we understand there is a constant ratio R. Okay, and geometric sequence is given by Tn equal to a r to the power of n minus 1, while r, the constant ratio, r is just Tn over Tn minus 1. So we can first find r, because otherwise we will have like two unknowns, r and n. Okay, let's first find the value of r. R will be equal to Tn. So if I choose 10 for my Tn, and then Tn minus 1 will be 30. Similarly, if 10 over 3 was my Tn, then Tn minus 1 will be 10. But I prefer to take 10 as my Tn, and then Tn minus 1 will be 30. So it's going to be like 10 over 30. Then r will be equal to just 1 over 3. So this is the value of r. Then we can write Tn as the first term in the sequence, which is 30. So say 30 times a times r, which is 1 over 3 to the power of n minus 1. But now the question says that Tn is given. It is the value that you can see 10 over 729. So I can type in now the value of Tn. So let's just do it this way. See? So now this will be 10 over 729 will be equal to 30 times 1 over 3 to the power of n minus 1. Now, it is good when you see questions like that. It is good to try to write all the numbers in terms of the prime factor. Prime factor, I mean, you write the base, okay? A base must be a prime number with an exponent. So now, I can say that 10 cannot be written as in terms of a prime factor, but 729, yes, we can, but let's see. We can write like this, 10 over 729. Let's first change over here, or maybe before even I say that, let's just see if we can write 729 in terms of its prime factor. You can just take a calculator. You can just take this calculator like this. Okay, hold on. I'll move it here. So we can write 729 and then press equal, and then press shift, okay, and then press effect. Then we can write 729 in terms of its prime factor. So this will be good as 3 to the power of 6. So and then 30, I can already see I have 30. So something like 3. I can write 3 times 10, okay, and then 1 over 3 there. So I can write, instead of writing 30, I can just write 3 times 10. I know that's equal to 30, okay? And then 1 over 3 can be written as 3 to the power of 1 or to the power of n minus 1. Why? Because one of the law of exponents says, remember the law that says 1 over a to the m equal to a to the negative m, okay? So you will notice we have 10 here and then 10 there. We can simplify. We're allowed to simplify to cross because they are products. This here is products, and then that's separated by the equal sign. We allow to simplify to cross this 10 and that 10. So this is 1 over 3 to the 6 equal to 3 times now what? Over here, that because you have like 2 to the negative 1, this will be 3 to the negative n plus 1, because the law of exponents says a to the m all to the n equal to a to the m times n. So we can times the exponent. And now 1 over 3 to the power of 6, according to this law here, we can write it as 3 to the power of 1. I mean 3 to the power of negative 6 equal to, and then according to this second law, not that law, but I want you to notice that here is 3 to the power of 1, okay? So in this situation, we can just write 3 and then add the exponents. It's going to be like 1 minus n plus 1. And then this makes 3 to the power of 6 equal to 3 to the power of negative n plus 2. I prefer to move my board over here. 3 to the power of 6 equal to 3 to the negative n plus 2. Now, in this situation, the law says this. If we have like a to the m and then equal to a to the n, situation like this, when we have equations, we can just drop the basis and then equate the exponent, make m equal to n, okay? M equal n. Now, over here, we can just cross this basis, 3 and 3 there, and then this will be 6 equal to negative n plus 2. And then I prefer to move n over and then 6 on the other side. So, okay, I omitted the negative sign here. So negative 6 and negative 6 there. So negative 6, yes. I can just move the negative n over and then move the negative 6 over. And then this will be, n will be equal to positive 6 now plus 2. And that makes n equal to 8. So therefore, so that's n, okay? Therefore, it's T8, which is equal to 10 over 729. Okay. The following question, what's that? Let's see. That was 2.1.1, now 2.1.2. The question says that calculate 30 plus 10 plus 10 over 3 plus dot dot dot. Now let's do this sum. Oh, you're welcome. Now right here, question 2.1.2. So we want Sn of a geometric sequence, and then we do know that the geometric sequence Sn is given by A, open brackets, excuse me, yeah, 1 plus r to the power of n over 1 plus r. But we noticed that we also did find that r was equal to 1 over 3. Okay, so if r is equal to 1 over 3, this is the type of what we call a convergent geometric pattern. Okay, say since r equal to 1 over 3, 1 over 3 is between -1 and okay, let me write it this. I prefer to write it this way. Okay, since r equal to 1 over 3, okay, the formula says that -1 less than r less than 1 implies that we have a the series converges. Therefore, Sn is called the S sum to the infinite, which is given by A over 1 minus r. So in this situation, we can just say S infinite will be equal to A, which is 30, the first term of the sequence, over 1 minus 1 over 3. Now, S infinite will be equal to 30 over 2 over 3, and then S infinite will be equal to 30 over 2 over 3. This is equal to 45. Well, let's see, it's going to be 30 times 3 over 2, and then this is equal to 45. Thank you. That was question 2.1.2. All right, thanks.